All right, welcome everyone. We'll get started here in a minute, but while you're waiting, if you want to write in the chat where you are tuning in from in the world, that would be awesome. We are here in Austin, Texas, but we would love to know where you guys are all joining in from. Cool.
Awesome. Hi, Jeff.
England, Southport, England, Buffalo, New York, Charleston, South Carolina, Toronto, Canada, India. That's awesome. Oakland, California, Connecticut, Nigeria, India, Honolulu, London, hi from Belgium. This is awesome. It's great to see, yeah, in different parts of the world. France, New Jersey, Atlanta, Georgia, Virginia. It's awesome. We'll give people about 1 more minute, and then we'll get started. New York, Anchorage, Alaska, Asheville, North Carolina. Hi, Mom. California, San Antonio, Cleveland, Ohio, Colorado, Brazil. That's awesome. Pennsylvania, Bangladesh. Cool. Another one from England, California. Awesome. Okay. I think that's one of my favorite parts is just to see how many people we have from all over. But yeah, we'll go ahead and get started. My name is Lindsay, and I have started Dark Energy Explorers in 2021. And today we are really excited to have a tour for you guys of the Hobby-Eberly Telescope. And we will are still doing this event for you guys to celebrate Citizen Science Month. It's all month of April. And if you guys aren't familiar with citizen science already, if you're a dark energy explorer, you know all about citizen science. But essentially what citizen science is getting the public involved in a research project. And so getting you guys involved in our dark energy experiment here at the University of Texas, Austin, and just collaborating as the general public. Hopefully you guys learn some things, and then we get those classifications from you guys, and you guys have been a tremendous help, and truly this research would not be able to be done without you guys. And so if you aren't a dark energy explorer already, you should be. And so you can become a dark energy explorer. We're hosted on Zooniverse, which is an online citizen science platform. We have a mobile app, as well as you can access via whatever your desktop is. And so what we are doing with our citizen science project is we are letting you guys be a part of this project and be astronomers. We'll teach you how to classify the galaxies, stars, meteors. You'll see all different kinds of things with the data that we get from the telescope that you're about to tour. And we let you guys look at this, and then we do some research with it, and you guys have been truly awesome and really helped us out a lot, and not to mention are almost as good as we are at doing this. So we really, really appreciate it, and thank you guys for helping us out, and we hope that you enjoy this event as part of our thank you to you, that we want you to be able to see the telescope that you are looking at the data from, and so we appreciate all of your help. So I just want to introduce our team. If you are a dark energy explorer, you mainly interact with just the app or the desktop. And I would love for you guys to put some faces to the names for our team here with the Hobby-Eberly Telescope Dark Energy Experiment. And so Carl Gebhardt, who is my advisor, and he is the lead of the Hobby-Eberly Telescope Dark Energy Experiment. He is on our call here. If you want to learn more about HET and learn more about what we're doing with the classifications from Dark Energy Explorers, you should go watch our last YouTube video that we did a few months ago. It talks all about that, and you'll definitely have a great background after you see this awesome tour that we're going to get from Stephen. We have Erin Cooper, who is our data manager and truly a wizard with the amount of data that she deals with that we get from our telescope. Keely Finkelstein, she is an astrophysics professor here at UT Austin, as well as does a lot with the education work at McDonald Observatory. Then we have Laurel and Dustin, who are also graduate students here at UT Austin and do a lot of work for the Dark Energy Experiment. And like I said, I'm Lindsay. We also have a great undergraduate team who have helped us a lot, especially with putting this event together. Jose and Mike and Isaiah are doing various work within Dark Energy Explorers and working on our user engagement and helping with you guys, as well as Jennifer. She is working with some of the HET data and looking for Pluto clusters. And so we want to showcase this team here that's in Austin or within the HET team. But we also, you guys are a part of this team as well because you're also classifying the data. So we just want to say thank you and remind you guys that you really are a part of all of this data that we're doing. And so if you guys tuned into our last Zoom call, we held a sticker design competition, and we were overwhelmed by the amount of people that decided to take their time, and we didn't know we had so many artists out there. But we really appreciate everyone who participated, and we want to announce the winners. And the winners will definitely be getting stickers of their own design, but we want to give everyone on this call the opportunity to be mailed a sticker. They've already been printed. And so without further ado, I want to announce our winners. So congratulations to Michelle and Giannis. I think that they are both on this call. These are their two designs here that we got printed, and we here in the HETX team just loved how you guys incorporated some of the actual data that we have that's a part of the project. That's part of that blue background. So it was really cool to see everyone's design. But we want to make sure you guys fill out the survey at the end of this call, and so that we can enter you in to be sent one of these stickers so that you can have an official Dark Energy Explorers sticker. All right, so why you all are here, we have our tour of one of the largest telescopes in the world, and I am super excited. I have gotten one of these tours from Stephen, and it is really, really cool, just the amount of work that goes into how this telescope operates. The Dark Energy, or where the Hobby-Eberly Telescope is in the world. So we are out in West Texas. And so you can see we're right here in Jeff Davis County in the Davis Mountains in West Texas. So whenever we go there from Austin, it takes us about 7 hours to get there. And we have it there because we need really, really dark skies. And you can see this middle picture here is a map of the United States and all of the light pollution. And where the McDonald's Observatory is, you can see the really dark area, which is where we need those nice dark skies. And you can see kind of the map of all of the cities and where all of the light pollution comes from all over the world. And so McDonald Observatory actually sits in the largest dark sky reserve in the world. And what we call a dark sky reserve is where we try to protect the land where we have really limited light pollution. So if you guys live in large cities, it's probably really hard to see the stars at night. But if you live in places that are really a lot more remote, you might be able to have seen the stars at night, even the Milky Way. I would love to know if you guys have ever seen the Milky Way with your own eyes and where you were in the world, because truly it's getting harder and harder for us to be able to see the Milky Way with our own eyes because of all of the light pollution. And so the Dark Sky Reserve, where McDonald sits, is actually the first one that crosses international borders. So it takes up part of West Texas, but also into Mexico. And they're working really hard to protect those skies. All right, so the telescope that you guys are about to see, here is it in relation to a lot of the other large telescopes in the world. So the Hobby-Eberly Telescope is the third largest telescope in the world. And here it is on a map. Down here for scale, we have a tennis court and a basketball court, and then a human down here at the same scale. So truly, really, really large. These three telescopes here, you might be wondering, you know, those look a lot bigger than the Hobby-Eberly Telescope here. Well, you read the fine print, these say planned for 2027 and 2029. So they actually haven't been built yet, but they are in the works. Here is the famous James Webb Space Telescope that you might have seen or heard about in the news. So you can see the Hobby-Eberly Telescope, those mirrors are much, much larger even than the James Webb Space Telescope, which is pretty cool. Here is an image of HET, but I'm gonna leave that to Stephen to explain, and we'll talk about it a little bit more. And before I hand it over to him, I want to show you guys a little bit, because this is a virtual tour and you're not getting the joy of, you know, driving up and seeing HET in person. I want you guys to imagine that you have driven hours and hours in the Texas desert, like we do here from Austin. It's about a 6.5, 7-hour drive, and you've driven through the desert. And then you're climbing through the Davis Mountains, and all of a sudden you start to see the HET telescope off into the distance. And this is what it might look like. So there's that beautiful mirror that we'll see here shortly from above with the dome open. Awesome. Cool.
Nice.
Oops. All right. So yeah, without further ado, I'm going to hand it over to Stephen. He is one of our staff astronomers at the Hobby-Eberly Telescope. He lives on the mountain with another 4 astronomers that take these observations every single night and live out there full time. And he can tell you more about that. But yeah, without further ado, I will hand it over to Stephen for our tour.
Yeah, thanks, Lindsay, and thanks for setting all this up. We're excited to show you around today. It is kind of a hard place to get to, so I'm glad to see you coming virtually instead. So as Lindsay said, I'm Stephen. I'm one of the astronomers here. We have a whole team of experts who live on site and do all of the nightly observations in sort of service for the astronomers and citizen scientists who use the data when it gets analyzed. So I'm coming to you from the control room of the Hobby-Eberly Telescope. So we have a couple different camera views set up in here, but I'm at the desk where we sit all night long, every night doing the observations. And we're gonna take you around a couple different spots in the observatory here and show you some of how the telescope works and a little bit about it. Lindsay, can you go back to that image of the telescope? That's what I wanted to point at just to begin with. Or I can maybe even share. If that's, yeah. that's easier. So the Hobby-Eberly Telescope is unusual and really a novel telescope design. Like you can see on that picture, it has an 11-meter primary mirror that's made up of 91 hexagonal segments. This was one of the first telescopes to use segments. It's too big to make one single mirror 11 meters across very easily or effectively. So we use lots of small segments. But the most unusual part about this telescope is that it observes at a fixed elevation above the horizon. So it can't tilt its head up and down. It only rotates around. And so when the telescope is observing, we're observing about 55 degrees above the horizon at night. So we have to be very careful in our planning to observe targets, galaxies, stars, whatever, that are at the right elevation in the sky. But since the Earth turns, most of the sky is available to us throughout the course of a night or a year. So while we're observing, the telescope mirror is stationary, and what we move is actually the focal plane. So the telescope mirror collects light and it focuses it to a point where we measure that light. And for us, the telescope mirror itself is stationary while we're observing, and the focal plane moves to catch the reflection. So that movement I'll show you when we go out into the dome in just a minute, but I wanted to, with this picture, it's kind of good to see from the outside. We're going to go down into the dome next, but you're going to be kind of like surrounded by telescopes. So it's good to get your bearings here. You'll see the shiny mirror, that big curved shiny part. Then on the sides of the telescope are the two virus spectrograph enclosures. And you all know lots about virus as a spectrograph already, but you'll get to see all of the boxes that hold each of the spectrographs. And then shown in this picture in green, in real life, they're black. There's bundles of fiber optic cables that carry the light from the focal plane all the way down to the spectrographs. And so we'll see all of that, but sort of from underneath in the dome. Lindsay, if it's all right, I was thinking of going down into the dome. It's going to be noisy in there at first because we're running the air conditioning to keep it at the nighttime temperatures. We don't want all this metal to get warm in the daytime. But it'll take me just a minute or two to walk down there. And if you want to do any brief questions and answers, then I'll get set up on the mirror platform ready to show you that next.
Yeah, that sounds great, Stephen. So I will stop sharing, but yeah, if you guys have any questions, feel free to put them in the chat as we go along through the tour with Stephen as well.
Someone asked how large a telescope can get, and if you make an individual telescope out of glass, we pretty much reach our limitations because you just can't make glass that big. It gets too heavy, so you make it individually. The biggest telescopes we have are basically using the whole Earth, and that's in radio. They take telescopes spread around the Earth and take data from them, and then they bring that data together. So the biggest one we have right now is the size of the Earth, which is pretty awesome. And that's what made that remarkable picture of the black hole in at a nearby galaxy.
Okay, I don't know if you can see the dome floor camera from here. That would be a good one to show.
Awesome.
But I'm standing up here on the platform just underneath the telescope mirror. And hopefully you can see if I wave on that platform. Is that working okay?
Yeah, it looks great.
Okay, good. So that's the real telescope in person. We've got all the mirror segments. And then I think on that camera view, you can just barely see the spectrographs going up on the sides. But what I wanted to do is go extremely close and personal up to the mirror here. So if you can see my phone camera now, I'm walking up right up underneath the very edge of the telescope mirror. And so you can see the blue kind of jungle gym structure is all of the supports that hold the mirror. The mirror has to stay aligned to really high accuracy. You know, we move it in sort of 10 to 50 microns at a time. So really, really tiny movements. So that holds it all very stable. I'll get up closer here. It's notoriously hard to see mirrors because they're reflective, but you can see, you know, the segments there. I'll sort of pan across. If you see any curvy looking beams, those are reflections because the telescope beams are all pretty straight. But, oh, and I see some of the comments. I can tell you a little bit about the weight. Each mirror segment weighs about 300 pounds, and then there's 91 of those altogether. So anyway, so we're looking up here. You look sort of up to the side, you can see the virus enclosures, the spectrographs there. That's one set of them on that side of the telescope. And then just above those, you can see that big black bundle of cables going up to the tracker. I might be able to use, I don't know if that shows up very well, but I have a green laser light shining. That black bundle of cables goes all the way up to the tracker up there that moves our focal plane. Yeah. So then the other virus enclosure is on the other side, but I'm going to step down from here because I want to show you a couple of the ways that we move this telescope at night. So I'm going to step off of the platform. The first motion I'm going to show you is how the tracker moves. So while we're observing at night, the mirror is not moving for a given target, but what we move instead is the focal plane. And if I've got my hardware set up right, I should be able to just click a button and it will move. Okay, I'm going to aim my camera up a little bit higher. So the dome floor camera. If you could hear, the zoom might be cutting out some of the sound, but the gigantic many-ton structure is moving up overhead, moving sort of from the bottom of its range up to the top. And this is what it would be doing all night long while we're observing targets. So it's moving with really, really high precision. It moves to track the reflection of objects in the mirror, and it moves, you know, extremely accurately. It's a little hard to see from this far away, but it has a lot of sophisticated electromechanical components that help it stay exactly on target. As it moves over the mirror, it has to tilt at different angles, and it has to rotate, and so it's a very sophisticated system. So now it's all the way up at the very top, and you could probably tell as it moved, the virus cables, all the IFU bundles that come down from the telescope were moving with it. So that's one of the huge advantages to using those fiber optic cables, that we can move them, or the telescope can move and still stay connected as it moves. So give it another move down here. And I'm going to try something. Tell me if this works. I'm going to move another part of the telescope. And I'm going to wait to see if you can figure out which part of the telescope is moving. Just started that going, so keep your eyes out and try to tell. So the tracker is currently moving down. It's getting lower towards the bottom, but another thing will start moving here.
Yeah, I think your volume is going a little in and out, but I'm imagining that's just because it's a little loud right now.
Oh yeah,
the dome
okay,
is
sorry.
moving.
Yes, exactly. It does get loud when the dome starts moving. Yes, exactly. So hopefully you can sort of see all those little triangular shapes moving in the background there. So part of the dome opens up at night. You can see from that lovely drone video that we have a nice dome shutter. And actually right now, the dome shutter is right above the telescope. So that whole section of the dome there opens up, it slides off to the side at night, and that lets us see out like you saw in that drone video. And the opening in the dome is just barely big enough for the telescope to see out, but that's okay because the telescope doesn't move while we're actually observing at night. So you're seeing it spin. You can see that yellow That yellow machine up there on the top of the dome is our dome crane as well. We use that to lift any kind of heavy things in the dome. And they were using it actually just before we started today. We have a team of folks who maintain the telescope mirror. So each of those 91 segments needs a lot of maintenance. Usually once a year or so, we take a segment out of the telescope, recoat it with a fresh layer of aluminum, and then put it back in. And they were doing the put it back in part of that process today. So we have, that's where we're going to visit next after the dome floor. Is I'll show you where we do the mirror recoating. But they were, until about 10 minutes before we started, they were actually finishing up today's work in here to move the old mirrors out and to put some fresh mirrors in there. I think this telescope is really highly competitive to get access to at night if you're an astronomer. And I think what most astronomers don't realize is that it's also highly competitive in the daytime to get access to this telescope with so much work going on to maintain and improve. It's always a busy work environment in here. One of our electrical engineers is running around as well. I think he's avoiding the camera, but there's always work going on day and night at this facility. So let me adjust this camera down. The last kind of motion I want to show you out here. That's a good view. So we said that the telescope itself doesn't move to observe targets. So what we do move is between targets. So when we're finished observing at this position, then we would move over to a different position and observe, and we'd rotate the whole structure of the telescope. So on the phone view, we've got these feet basically on the telescope. It's got 16 of these square feet. They ride on top of this really, really smooth concrete pier. It's our nice smooth surface that the telescope sits on. That's one of the flattest pieces of concrete in Texas, I've been told. I don't know who keeps track of that, but they float on here on compressed air. So there's an air hose connected to each one of these pads, and it's basically a standard industrial pneumatic air bearing, or like a tiny hovercraft. This is an example of one that's on the ground here, just an extra spare one for demonstration. It's like a big rubber bladder. We pump in a whole bunch of compressed air to that. The telescope lifts up and floats like a hovercraft, and then it can rotate pretty quickly. So I'm gonna grab our hand paddle control here. And if I've done it right, this should make a loud noise, but Zoom is pretty good at cutting that out. So I'm gonna inflate these air bearings. So it is really loud in here right now, but maybe not obvious. And you should be able to see, especially on the camera, that the telescope has lifted up. And I'm gonna give it a little bit of rotation here. All right. So if you can see on my little camera, there's a small red wheel in there. That's the drive wheel that's making this whole thing go. It's just a teeny little electric motor. Once you've got it floating on air, it really has almost no resistance. So I'm gonna stop it that way.
I remember whenever I saw this for the first time. I was just going to say that I feel like you told me the analogy is similar to like an air hockey table. If you guys have ever seen an air hockey table and how quickly they can move across it, that's essentially.
Exactly. And I think the air pressure bearings are a really good example for us as well of technology that we did not invent. This telescope used a lot of off-the-shelf technology. So these are pretty standard in like industrial warehouses to move pallets around. It's pretty standard technology. So I just turned it off and we can watch the feet sit down here. We've got a good safety warning there that says do not, stick your finger under here. But so those are deflating and the telescope is sitting down, and yeah, you can see I left it pointing in a slightly different direction. So we'd be looking at a different part of the sky at this point and able to do our next observation over there. when we do this at night, all of that happens simultaneously. So time is really precious when you're observing at night. Minutes are valuable. So we are moving the telescope, moving the dome, moving everything into position so that we can be ready to do our observation as quickly as possible at night. Okay, I think I want to show you just one more thing on the mirror before we go to the next step here. Let me get this switched. So we talked, I think, and some people even asked as well, the good question about how do we clean the mirrors. So first I want to motivate why we need to clean the mirrors. You can see up in the telescope, if I go up close here again, I hope it comes through. Some of the mirrors are sort of hazier and some of the mirrors are sort of shinier. So the shinier ones have been recoated more recently and the hazier ones are older. So some of our oldest segments have been in the telescope for almost 3 years. We try to get them done every year or so, but with the pandemic and some staffing shortages, we've gotten a little bit behind, but we're making good progress to catch up. But you can see some of them are very shiny and some of them are a little hazier up here. So like I was saying earlier, about 2 segments every week or 2 come out of the telescope. We've got some spare segments that we use, and they get recoated. So we use that dome crane to use it kind of like a claw that comes down and picks up the mirror segment and takes it out. And I'm oversimplifying because that's like an all-day process, but takes out a mirror segment, and then we take them down to our mirror coating facility, which is where I'm going to walk you down to next here. But before I leave the dome, I got to turn the air conditioning back on because it's going to be another cool night and we need the system to be at the right temperature. So excuse me just a moment. Oh, that's amazing. Okay, thanks, Jim. All right, so we're going to walk next to the mirror coating lab. So they bring down a mirror out of the telescope. They put it onto this kind of cart. They wheel it in there, and then I'll show you where we take those mirror segments. So you take the mirrors out of the telescope and bring them back into our coating facility, which is abandoned at the moment. I think they knew we were coming. So I can show you what these look like. So this is one that came out relatively recently. These mirror segments are about 1 meter across, so 3 feet across, and they're 200 or 300 pounds or so. So it takes an overhead crane just to move them around at a basic level. So we have to first take them off of their frames. So each mirror sits on a pretty sophisticated metal frame that positions it really accurately. So we take the mirror off its frame so that it's just a piece of bare glass. And then it actually goes into this room, which has a stop do not enter sign. And this is the room where they get acid washed. So we use a special kind of strong acid and some very sophisticated sponges to do a really careful job of scrubbing off all of the aluminum from that coating. And that gets the mirror down to be bare glass. Then go back into here. This all happens in a clean room after this because we don't want any contamination on the mirror. So bring it all the way back to here. So this is a view into our coating room. So after the mirror has gotten all of its aluminum washed off, it goes into that big vacuum chamber back there, the silver tank. That tank is just big enough to hold 1 mirror at a time. We hang it upside down in the tank and then basically melt down some aluminum. It's about the amount of aluminum that would be in a paperclip if paperclips were made of aluminum. Just a 10 or 20 grams of aluminum, I think. Melt that down, pump out all the air so it's a vacuum, and effectively you vaporize the aluminum so that it goes up as a vapor and sticks to the mirror and gives you a fresh coating of aluminum. It's only a couple hundred atoms thick after it's coated on the mirror, so it's a pretty remarkable process. we have some pictures on the wall in here of just what it looks like. Everything inside that chamber gets illuminized, so everything gets pretty shiny when it comes out. But so that whole process takes 3 or 4 weeks per mirror segment, but we've always got some mirror segments in the pipeline working their way through the process. So the team of folks doing the mirror work are always busy processing the next segments and getting it going. But I think I should put these back away. They had a clean one in here this morning. I was going to show you a clean one, but they put it back into the telescope, so that's fair. They've got room to do four mirrors at a time before they go back into the telescope. So okay, so you can walk with me. I'm going to walk back upstairs to our control room where I started. And then I think up there, we'll be happy to do maybe moderated questions and answers about whatever else. But as I walk up there, I'm going through some of the offices. So this is where the daytime engineers work. And they've all hidden away from the tour, but they're software engineers, electrical engineers, mechanical engineers. A lot of this telescope is a sort of custom hardware that doesn't exist anywhere else in the world. So we need a lot of specialized folks to keep it going. So, but yeah, I'm back here in the control room ready to do questions and answers, I think. I don't know if, yeah, maybe.
Yeah. All right. Yeah, Lindsay's setting up the slides again so we can go to that Q&A. There was a lot of questions. The whole Dark Energy Explorers team was trying their best to answer, but we will have more time for more questions, specifically also for Stephen that handles the Hobby-Eberly Telescope.
Yeah, thanks, Stephen.
Actually, yeah. If you want, the one thing I realized I forgot to include that I should have done, if that's okay, is everybody. A lot of telescopes have catwalks where you can like step outside and see the great expanse. And I was giving a tour to like second graders once, and they were interested in the telescope. But then when I went outside, they were like, "Wow!" So I learned after that you always have to like show outside. So if you could spotlight the phone one again, I'll just take you out on our back porch here and show you. Let's see, is that working?
Yes, we are looking for the microphone one for your phone.
Okay. Okay, excellent. So this is, if we need to go outside at night while we're observing and check on the sky conditions, we come out here and have a nice view to the northeast and can see the mountains, and sometimes there's some cows. A little bit cloudy out here today, but not terrible. And while we're out here, one of the things I didn't mention in the telescope dome is that we have to align all of those mirrors every night to make them act like a single mirror. And this tall tower that you're hopefully able to see here, it's actually next to the telescope dome. That tall tower has some alignment equipment in it that can measure the light coming to each segment separately. And then we can basically adjust each segment until they're all reflecting back to a common spot. And the other cool thing to see out here, I don't know if you can even see the whole thing, but that giant white cylindrical tank is our tank of liquid nitrogen out here. The virus spectrograph is a very hungry consumer of liquid nitrogen. We use that to keep the instruments at about minus 110 degrees Celsius. And so that's actually running through some of this plumbing here. We've got liquid nitrogen plumbing that feeds it all the way over into the telescope up to the virus enclosure, and it keeps virus cold. But it means about once every week or two, we have to have a semi truck come out here to fill up this liquid nitrogen tank. So a big old tanker truck comes all the way up the mountain and empties its load into here. So it's a cool part of the tour just to see how much liquid nitrogen we go through. But yeah, no, that's our nice view of the outdoors. So I'll bring you back into the control room. Okay, sorry. And I guess, yeah, I'm happy to do Q&As now. I think that's the last thing I forgot.
Yeah, Stuart, I don't know if you have time. Did you want to show maybe the piece of data?
Oh, yeah. That's a great
That'd be
idea.
awesome.
So, yeah. So Virus, as you all know, produces a lot of data, and it requires a lot of people to work on it. I can show you a HET-X observation we made last night, but I will warn you, it may not look like anything like what you're used to seeing. Like this is really the raw data. So when we take a virus exposure of one of the HET-X fields, this is what we see at night. This is what comes out on the raw end. So virus has many copies of the same spectrograph. So it has 78 spectrographs tonight, or last night we had 76 of those running and taking data. And each spectrograph produces 4 of these little boxes on here. So if I just zoom in on 1/4 of one spectrograph at a time, this is truly the rawest of the raw data. So Virus has many fiber optic cables that each measure a different patch of the sky. The light from each fiber optic cable goes through something like a prism that disperses that light into its whole rainbow. So this is the blue end of the rainbow and the red end of the rainbow. And each little horizontal stripe, each one of these lines, if I can draw easily, oops, no, each little line is a separate fiber on the sky. So this is showing us the light from one patch of the sky that is spread out from blue to red colors on there. So every line is a separate patch, and that's 1/4 of one spectrograph. And last night there were 76 spectrographs. So when you zoom out on all of them, that's a lot of data, and it's mostly empty sky. I think that's one of the strengths of HET-X. It's very unusual, but it's a blind, unpointed survey. So most of these are just blank sky if I flip through them. But occasionally you'll see some cases where a fiber has a really bright source that emits light at all wavelengths, which is almost certainly a star. It's pretty bright. It might even be saturated in there. But oh no, it's not saturated. So yeah, so that's a nice spectrum of a star. There are some folks who are studying stars in HET-X, which is a whole different project. But oh yeah, there's a very nice star. So when we're observing at night, we're not usually looking at this detail at the raw data. We know that there are whole teams of people who are ready to go analyze that data. And we take an exposure like this every 6 minutes whenever we're observing for HET-X. So at the end of the night, we could have 30 or 40 or 50 exposures like this, which each have, all that data in them. So we don't look at it, in great detail at night, but we rely on Lindsay and Carl and the whole team to analyze it the next day. So that's the very, very raw data view.
Thanks. And then I'll go ahead and share back these slides because I just wanted to kind of bring it back to where we are with Dark Energy Explorers. So if you guys have classified with us, you have now seen the data and you have seen even more raw data than before. And this is exactly what we are giving you guys within the project. So it's pretty cool that it comes right from HET, and now you've seen how the telescope works. But yeah, with that, I will leave it open for you guys. If you want to put more questions in the chat. I know there might be some that we missed. If you want to put it back in the chat or raise your hand and slightly unmute yourself, we will open it up for questions.
Give me 1 sec while I fix something before we do a Q&A section. Yeah, I'm just making sure that, all right. So yeah, if you have a question, put it in the chat and then we'll ask you to unmute as well. Just to prevent anything from happening. Please put your question in the chat, and then from there, we will choose you to unmute, put your camera on if you want to do that.
Yeah, I saw somebody was saying that they were thinking about wanting to visit Texas, and yeah, it's about an hour away from Big Bend National Park. If you guys have any interest in coming to see Big Bend, you should go visit McDonald Observatory and go to the visitor center for HET.
Yeah, the visitor center is open Tuesday through Sunday, and they have amazing tours and star parties, and there's a lot to see out here. Yeah. Can I just pick some of these, or do you want to choose, or how?
Yeah.
Well, okay, I saw one that I know the answer to, which is, are all those segments exactly the same size, shape, etc.? Yes, the mirror has 91 identical segments in it. This is a really unusual part of this telescope. Since the mirror doesn't move while we're observing and the focal plane does, the mirror has to be spherical. So it has to be as if it was a small piece of a sphere, so that we can move around to different positions and still get an image. Another big advantage of a spherical mirror is that all segments are identical. So if you're manufacturing something, it's a lot easier to make 95 or 96 identical copies than to make lots of different ones. And it also makes it easier when we re-illuminize segments. We can take a segment out of the top, coat it with new aluminum, and put it back in the bottom. It doesn't matter. They're all interchangeable. They're all identical. Now, the mirror team would know that each mirror segment has kind of its own personality, and it might have kind of its own, quirks and behaviors, but to a simple, basically they're all identical. They're supposed to be identical. And yeah, a couple of questions are about like what we do at night. And I think that's also something I didn't tell you enough about, which is that we observe in what's called queue observing. So it's like there's a long list of targets, and we are just going through them in order that we can. So no astronomers come here to observe their own observations. That's unusual. Most smaller telescopes, the astronomer goes there and operates it and then takes their data home. But here we have a list of all the approved programs that people have submitted to get observations. And we optimize what we can observe every night based on what's up in the sky. Remember, we only observe at 55 degrees, and also the sky conditions. So for HET-DEX, we can't observe when the moon is up because it's way too bright. So if the moon is down and the HET-DEX fields are at 55 degrees, we'll be observing HET-DEX data. But we also have our other major instrument is an infrared spectrograph that observes exoplanets around small stars. And so when the moon is up, we're not doing HET-DEX observations. We're usually measuring the radial velocities of exoplanet hosting stars with our infrared spectrograph. So this telescope is sort of an all-purpose telescope that can do all kinds of different science projects. So the person who asked how many projects do we collect data for on a night? It depends a lot on the night, but it could be up to 10 or 15 different projects, many of which are led by graduate students and postdocs and researchers at University of Texas and Penn State. And they will submit their targets and we'll do as many as we can. If we observe your galaxy one night, you'll get an email the next morning that says you've got data, and then you can go download your spectra that we took for the previous night. So it's a very convenient mode of observations that makes it easier to get really good data. Oh, and the question about photos that this telescope took, I also didn't mention. This telescope doesn't take any pictures, which is not too uncommon amongst gigantic specialized telescopes like this. But we work only in spectroscopy, so we take the light from astronomical sources and break that up into its colors, like the data you've gotten used to seeing for HET-DEX. You can make that into an image if you collapse, if you sort of flatten out all the wavelength color. If you just make it one color, you could get a picture of that little patch of the sky. But everything we do here is focused on spectroscopy. So like that raw data that you saw, it doesn't really look like a pretty picture. But they say if a picture is worth 1,000 words, then a spectrum is worth 1,000 pictures, because you get so much more information from a spectrum about the physical properties of the source, and everything that really goes on, temperatures, movements, chemistry, everything. You get that from spectroscopy. So, yeah. What other questions?
There's one question that is asking what the source that powers the whole location. I think it could be pretty cool to talk about just the community that you guys have on the mountain.
Yeah, no, that's a great point. We are in a really remote part of Texas. So we do have power lines that get the power to us here, but we also have on site a generator that's capable of running the entire HET for like a week maybe, because we do have very sensitive spectrographs that need temperature control, like really, really precise temperature control. And if you have a power outage and you turn off all the temperature controls, we start to really have problems. So we have generators, but also power. But then, yeah, like Lindsay mentioned, there's about 60 or 70 of us who live here down at the bottom of the mountain, mostly from where the telescopes are, about a mile down the road. And so we have a well for our water. We have a wastewater treatment plant that all the sewage processes through. We have telephone infrastructure and all the stuff that you would need basically in a tiny little town. We have for our own little site. So, I've showed you the very, very top of the observatory where the telescopes sit, but supporting that is a whole amount of infrastructure and all of the the physical plant staff and the technical folks who keep the toilets flushing and keep the power on. Like there's a lot to do for supporting a prestigious observatory beyond the spectroscopy. Basically, we are the end of a long chain. But yeah, it's like a little tiny community out here. If you need an egg, it's a 30-minute drive to the grocery store, and they close at 7 most nights or 8. So you just go ask your neighbor for a cup of sugar or an egg instead, because it's a long way to the grocery store.
While we're while we're wrapping up the questions, for those that are leaving early, I am gonna drop the survey link if you do want to get that sticker and give us feedback. So we're still gonna have a few questions left, but I am gonna drop that down on the chat. And if you have a mobile device, you can screenshot or scan the QR code, and that should take you to the survey as well.
Yeah, we'll hang around for a few more minutes if people still have questions, but yeah, thanks for joining. And yeah, again, you can use this QR code or the link that Jose just put in the chat.
So the question about how do you prevent warping from temperature change? And the answer is we don't. Unfortunately, we have to align all those mirrors in the telescope at the beginning of every night so that they act like one mirror. But then if that support structure under the telescope changes temperature by more than a degree or two, the telescope mirror will have gone sort of out of focus. And so we do have to then realign the mirror and use that alignment tower again to compensate for that. So that's why I was eager to turn the air conditioning back on, because we run the air conditioning all day to keep it at nighttime temperatures, so that when the sun goes down and the astronomer comes up and the telescope operator comes up for the night, as soon as the sun is down, we open up and we start aligning the mirrors and getting things going. So we want the temperature inside the dome to be the same as the temperature outside the dome. And yes, Amanda, that's exactly right. The different segments are raised at different angles because they all make up one big mirror. So the ones kind of up at the top have to be tilted a little more closer to vertical, and the ones near the bottom have to be kind of flatter to get the light up. But the curvature across each individual segment should sort of perfectly continue onto the segments next to it if they're all lined up perfectly. But it's challenging. and actually when the JWST first launched, they also had to align their mirror segments to make it act like one big telescope. And we were following along those efforts. It was pretty exciting to see because there's not too many different ways to align a telescope mirror. So they did it fairly similarly to the way that we do it. So we were watching as they were sharing like daily updates on how close they were getting to alignment. And we were thinking, wow, it takes us 20 or 30 minutes to align it, but it took them like 2 weeks. So, I mean, they were in space and they had a lot of other complexities, but aligning a segmented mirror is fairly similar for all of us. The environmental impacts question is a good one. We are very sensitive to the environment out here. As you saw, or as I talked about, at night we open up the dome, and so all the outside air comes in. So we have a strict set of limits on all the environmental conditions that could impact the telescope. So we have, I don't know if this will work. We have a weather system that's always tracking, kind of screwy, but we have a weather system that's always watching the outside conditions. If the humidity gets dangerously high, if the wind speed gets too high that it might break some parts, if the particle counts, if there's too much dust in the air, if the temperature is too low, some of our systems start to fail. So we have limits on all the different parameters, and we can only observe when those are all satisfied. So we lose maybe 30% of the year is lost to bad weather. Most of that's clouds, but in the wintertime, we can get some fog in the area as well. And high winds sometimes but yeah, about 70% of the time we're open taking observations at night. We're very protective of the telescope. As you can see, it's just very exposed. That whole mirror is exposed and the virus spectrographs are exposed and everything is just kind of out in the open. So we're very protective of that dome environment. And there's a little bit less pressure. If you are an astronomer and you were lucky enough to get 2 nights of time on some big telescope and you traveled halfway around the world to use that telescope and the weather conditions were just a little bit not quite great, you might think, I'm going to push through, I'm going to push the limits a little bit and try to get my night. But because we do Q observing, if the weather is not good, we will close up and we will come back tomorrow night and we will try again. So we really try to protect the telescope so that it's in the best condition possible to do the observations. We don't give up until like sunrise though. So if the weather's bad at midnight, we're here all night until the last possible minute. So we try to get every ounce of observations we can from this telescope. Yeah.
While we wrap,
No, yeah. Go ahead.
While we're wrapping up questions, I'm also putting the link once again for those that missed it out. But yeah, Stephen will still answer any question that was being said.
Yeah. Just that same environmental question mentioned fire hazards. We do live in a desert and it is prone to wildfires. So we're quite attentive on that. Out here, a lot of folks who live here also sort of support and serve their communities in different ways. So a number of our staff at the observatory are also volunteer firefighters or volunteer medics. We don't have like an official fire department, a municipal fire department, but we have a really strong volunteer fire department. And a lot of people step up when needed, basically, to help out. So it's a small community that really supports each other in a remote location. It's a special place. Do we become tired staying up all night? Good question. So most of the observers, when you work a night shift, you typically sleep in the daytime. So I don't find that it's tiring at night as long as I have slept well in the daytime that day. So I think some of our night staff are sort of permanently nocturnal and they really like staying up all night and sleeping all day. And this is a job where that's required. So if that appeals to you, think about finding a observatory job, because we are up all night. The work shift is sunset to sunrise. So in the winter time here, our winter nights can be 14 hours long or so. So that's a pretty long work shift. But in the summertime, it might be only 8 hours from sunset to sunrise. So it's a pretty easy night then. But yeah, that's part of the job.
Cool. Well, I know we could probably ask Stephen questions all night, but we will let him go. I know it's a few minutes past the hour, but we have really enjoyed this tour. I hope that you guys enjoyed it as much. I learn new things all the time, every time I see a tour of this telescope. But yeah, if you guys do have more questions, fill out the survey and put the questions in the survey. We'll try to get back to you guys, but especially if you want to try to be sent a sticker, please fill out the survey. But again, thank you guys so much for joining, and I will hopefully see you guys at our next Zoom call.